All chemical reactions can be placed into one of 6 categories: combustion reaction, single replacement reaction, double replacement reaction, synthesis reaction, decomposition reaction, and acid-base reaction. Over the next several slides, we will look at how to differentiate and identify each of these types of reactions. The definition of a combustion reaction is when oxygen combines with another compound to form water and carbon dioxide. These are exothermic reactions, meaning they produce heat. But how does one truly look at a reaction and determine that it's a combustion? Well, here's what we look at. First of all, a combustion reaction is a reaction where we take a hydrocarbon, meaning a compound composed of hydrogen and carbon, and we combine that with oxygen. So anytime we have a hydrocarbon plus oxygen, we will always make CO2 and water. And that's the definition of what a combustion reaction is. A synthesis reaction is when 2 or more simple compounds combine together to form a more complicated compound. And what we have is we have chemical A plus chemical B gives chemical AB. An example would be if we had iron plus sulfur, we would end up with iron sulfide. Here we have 2 individual elements coming together to make one more complex compound. A decomposition reaction is the opposite of a synthesis reaction. Here we take a complex molecule and we break it down to make 2 simpler compounds. Now it can be 2 or more than 2. Here we have water breaking down to make hydrogen and oxygen. A single replacement reaction, also known as a single displacement reaction, is when one element trades places with another element in a compound. Now, to determine which element trades places, we must check charges. Here we have our element by itself, magnesium, and here we have our compound, that's water, composed of hydrogen and oxygen. Magnesium, if we looked on the periodic table, has a +2 charge. Checking the charges of both hydrogen and oxygen, we see hydrogen has a +1 charge, while oxygen has a -2. Our like charges trade places. Therefore, our magnesium would join up with our oxygen. Now, this happens to be an unusual case where we have magnesium hydroxide formed and hydrogen gas. However, on most of our chemical compounds, we would see it as an element plus a compound, making a compound plus an element. Now, what element A trades places with is dependent upon its charge. If element A is positively charged, it will change with element B. If element A is negatively charged, it will change with element C. When we write out our new chemical compound, we must go back to our fundamental rules of writing out our formulas. We have to check the charge of chemical A, we have to check the charge of chemical C, and crisscross to get the correct formula. Also, don't forget to check on chemical B. Is chemical B a diatomic? Now, if chemical B is a diatomic, it would be written as B2. If it is not, then we just write our element symbol. Now, in a double replacement or double displacement reaction, we have anions and cations of 2 different molecules switching places, forming 2 entirely different compounds. These reactions are very colorful and are very enjoyable to watch. What we have is, if we will go back over, our cations are first. So our A and our C would be our cations. Those are positively charged. Our anions our second. Those are our negatively charged substances. And so we would have our like charges trading places. So A and C would trade places, and we would get chemical AD plus chemical CB. And we do have to go back to our fundamental rules. We check the charge of A, we check the charge of D, crisscross, get our correct formula. We check our charge of C, check our charge of B, crisscross, and get our correct formula. A classic example of a double replacement reaction is lead 2 nitrate mixed with potassium iodide. Both of these are colorless solutions, but when mixed together and the displacement occurs, a very thick yellow precipitate forms. So as we look at this formula right here, we have our lead 2 nitrate. Lead has a +2, nitrate has a -1, we crisscross, we get our formula. Potassium iodide, potassium has a +1, iodine -1, crisscross, we get our formula. Our lead and our potassium are our cations, or our positive charges. Our nitrate and our iodide are our anions, or our negative charges. So we trade places with the potassium and the lead. When the lead joins with the iodine, we need to check charges again. Lead has a +2, iodine -1, crisscross, we get our formula. Potassium has a +1, our nitrate has a -1, crisscross, we get our formula. So with these equations, our double displacement reactions always look very large and scary. However, they are very simple, as we just trade places with our two cations. Now our acid-base replacement reactions, it's a special kind of double replacement reaction where an acid and a base react with each other. To be an acid, a compound must begin with H, and to be a base, the compound typically has OH. And so what we have happening is we have a double replacement reaction where we have our acid, and here we have the H plus some anion, such as HCl. And here we would have our base, and we would have some cation plus OH. And so our positive cations trade places, and what we always make is water and an organic salt. So let's look at an example right here. We have HBr, this is our acid, it begins with hydrogen. Here we have NaOH, it has the OH indicating it's a base. So our hydrogen and our sodium will trade places. That will give us HOH, or water. And then we have our sodium and our bromine. Now again, remember, sodium has a +1, bromine has a -1, crisscross. We will be spending more time reviewing over acid-base reactions when we reach that particular chapter. So with so many different types of chemical reactions that exist, how can one look at a reaction and identify exactly what type of reaction is going on? Well, I know that the classic example is, does your reaction have oxygen as one of its reactants and carbon dioxide and water as a product? But let's review over this. Does your reaction have a hydrocarbon, a compound that's made up of carbon and hydrogen only? And is that reacting with oxygen? Are your products carbon dioxide and water? If that's the case, then a combustion reaction is taking place. Do you have two simple chemical compounds or two simple elements coming together to make one complex chemical? If that's the case, then we have a synthesis reaction. Do you have one large molecule and it's being broken down, so we have a large molecule as our reactant and our products are two simpler compounds? If that's the case, then we have a decomposition reaction. Do you have an element by itself plus a chemical compound as a reactant, and then the product has a new compound and a different element by itself? If that's the case, then we have a single replacement reaction. Do you have two big scary looking compounds as reactants and two completely different big scary looking compounds as products? Well, then you have a double replacement reaction. And finally, for an acid-base reaction, do you have a chemical compound that begins with hydrogen plus a chemical compound that has OH in it? And are your products water and then a salt, a chemical that's combined typically with a halogen? If that's the case, then you have an acid-base reaction. So this would be a good point to just press pause and go through these sample problems and see if you can identify what type of chemical reaction is occurring. So press pause, do the practice, and when you're ready for the answers, press continue. Well, let's see how you did. Number 1, we have NaOH plus KNO3 yields NaNO3 plus KOH. On this, we have two chemical compounds as reactants and two completely different chemical compounds as products. And notice that all we have done is we've taken our potassium and sodium and traded places. Therefore, number 1 would be a double replacement reaction. Number 2, we have a hydrocarbon plus oxygen yielding carbon dioxide and water. This would be a combustion reaction. Number 3, we have an element by itself plus a chemical compound yields a new chemical compound and an element by itself. Therefore, we have a single replacement reaction. Number 4, we have a large chemical compound plus a large chemical compound, and it gives two new chemical compounds. And when we examine our products, we see that our calcium and our magnesium have traded places. Therefore, we have a double replacement reaction. Number 5, you'll notice that we have a compound beginning with H, so we have an acid. Here we have OH, so we have a base. We are making water. So here we have water, and we have a salt forming. On number 6, we have an element by itself plus an element by itself. Now notice that we have O2 because oxygen is diatomic. We also had it appear up here. And when we had these two elements by themselves, they come together to make a more complex chemical compound. Therefore, we have a synthesis reaction. And finally, on number 7, we have a chemical compound, sodium carbonate, breaking down to make two simpler compounds. Therefore, we have a decomposition reaction. So how did you do? If you have any questions about the sample problems 1 through 7, please stop by my classroom and I'll be glad to go over this in more detail.